Good morning to everybody. Uh, this is the sixth class of Physics 2, Electromagnetic Field and Induction. Actually, we'll discuss in this class what is magnet, the properties of magnet, and what is the magnetic field, what is the magnetic induction, and what's the electromagnetic field. Uh, Actually, the main contribution of Biot-Savart's two scientists, famous physicists, and Ampere and Faraday also. So in this lecture, first, we'll discuss also the Lorentz force law, Biot-Savart's law, Ampere's law, Faraday's law, and application of them. We also discuss the application of Biot-Savart's law, Lenz law, and induced and in induction and self-induction. And we will also discuss some derivation of important formula and law. So welcome to everybody. Okay, first of all, what is magnet? Actually, magnet is the material or object that produces magnetic field. So we'll discuss the magnetic field, but before that, we'll discuss what is magnet. So a magnet is a materials or object that produces magnetic field. This magnetic field is invisible, but is responsible for the most notable property of magnet. A force that pulls on her ferromagnetic materials, such as iron. Iron is called actually ferromagnetic materials, and it creates highest magnetic field. This is why it is called ferromagnetic, and attracts or repels other magnet. So this is the example of attraction and creating magnetic field. Now, what is the magnetic domain actually? So iron and other ferromagnetic substances though are different, the atomic makeup is such that smaller groups of atoms band together into areas called in which all other electrons have. So the domain at which the magnetic field created is called the domain of magnet. If we put that piece of iron within the magnetic field through the domain, all begins to point at the same direction. Okay, so and for this domain, the magnetization created before magnetization. So all atoms and all the direction of all parts of magnets are different, but after magnetization, their direction and north pole or south pole create. So this is the actually magnetic domain. Now, what are the properties of magnets? So this is there are 5 interesting properties of magnets. Magnets attract a object of iron, cobalt, and nickel. That means metallic substances is attracted by the magnets. The force of attraction of a magnet is greater at its poles than in the middle, because there are south pole and north pole at a magnet. So in the middle there will be no attraction. Like poles of two magnets repel each other, opposite poles of two magnets attract each other. We must know from our beginning of study. So if a bar magnet is suspended by a thread, and if it is free to rotate, its south pole will move towards the north pole. This is the actually properties of magnet. Now, what is the magnetic dipoles? So every magnetic is a magnetic dipole. So every magnet, because it has two poles, one is north pole and south pole. So if a magnetic piece of a steel rod is cut into smaller pieces, each piece is treated as a magnet with a north and or south pole. So therefore a magnet can be said to be made of lots of tiny magnets all lined up with their north poles pointing in the same direction. At the ends of the free poles of the tiny magnets repel each other and fan out. So the poles of the magnet are around the ends. So the magnetic monopole does not exist. That means with single pole, there will be no magnets. So if in any magnets there must be two poles, one is south pole and north pole, and there are a line of forces which is called magnetic line of forces, and it will come out from north pole and enter perpendicularly in south pole. Actually, in our previous lecture, we have studied about the electric line of forces. It's also the same as that, the magnetic line of forces, and it's come out from perpendicularly from north pole and enter into the south pole. So, and all magnetic line of force does not intersect each other. So what is the magnetic field? A magnetic field is the area around a permanent magnet or a wire carrying a current in which a force is experienced. So also called magnetic flux density. That means units will be Weber by per meter or Tesla. This is the actually um, unit of magnetic field. The direction of the field at any point should be the direction of the force on a north pole. You have to remember this. The direction is shown by the arrows here. Actually, this is the example graphical depiction of magnetic field lines. There are two piece of magnets and attract each other, north pole and south pole, but north pole and north pole will be repel each other. Okay. Now, what's the magnetic flux? Magnetic flux can be defined as the measure of magnetic field in a certain medium. In simple terms, if the magnetic field had to pass through a certain medium, it will always travel as flux lines. Flux lines are imaginary lines, but the continuous lines travel from north pole of magnet to its south pole. That means this is the actually line of forces, magnetic line of forces, which is coming out from north pole perpendicularly and entering into the south pole also perpendicularly, and don't intersect each other. All imaginary lines will not intersect each other, and the unit of magnetic flux is Weber. Now there are two types of magnet. One is permanent magnet and another is electromagnet. A permanent magnet is an object made from materials that is magnetized and creates its own persistent magnetic field. As the name suggested, a permanent magnet is then permanent. That means it will be never losses the properties of magnetism. This means that it always has a magnetic field and will display magnetic behavior at all times. On the other hand, an electric magnet is made from the coil of wire, which acts as a magnet with an electric current passes through it. Often an electromagnet is wrapped around a core of ferromagnetic materials like steel, iron, etc., which enhances the magnetic field produced by the coil. That means this is a solid local like a solenoid, and south pole, this is the south pole, and this is the north pole, and this is the iron core. So the and from north pole enter coming out the magnetic line of forces and entering into the south poles. That means um, magnetic field created due to the force of magnetic line of forces. So this is also the properties of magnetic line of forces and magnetic field created. And this is the example of electromagnetic field. Now, permanent magnet versus electromagnet. Actually, there are a little bit difference between these two types of magnet properties. Permanent magnet has persistence magnetic field, and electromagnetic field magnet only displays the magnetic properties when an electric current is applied to it. So magnetic strength and advantages. There are another two properties. Magnetic strength. Permanent magnetic strength depends upon the materials used in its creation. The strength of an electromagnet can be adjusted by the amount of electric current allowed to flow into it. That means more flow of electric current will produce more strength electromagnetic field, and less current also create the low magnetic field. So the main advantage of permanent magnet over an electromagnet is that a permanent magnet does not require a continuous supply of electrical energy to maintain the magnetic field. However, an electromagnet's magnetic field can be rapidly manipulated over a wide range of by controlling the amount of electric current supplied to the electromagnet. So this is the main three um, relation between permanent magnet and electromagnet and their comparison. So laws of electromagnetism we have to discuss. There are four fundamentals electromagnetism laws. First law is the Biot-Savart's law, which is applied in the magnetic field generated by the current in wires, and also Ampere's law, the effect of a current on a loop of flux which it threads. Force law, the force on an electron moving through a magnetic field, actually Lorentz law of forces. And also we'll discuss Faraday's law, the voltage induced in a circuit by the magnetic flux cutting to it. That means it's applied in the induced induction or self-induction. So now we will try to understand about the laws of electromagnets and their fundamental. Okay, now what's the actually magnetism? Since the ancient time, certain materials called magnets, and we have discussed about these magnets and properties, which have been known to be the property of attracting tiny pieces of metal. This attractive property is called magnet. So this is a bar magnet and also U-typed magnet, and both magnets has south pole and north pole, and it has also north pole and south pole. So which is attracted by property the property of magnets. So this is called actually this property, this attractive property is called magnetism. Now, what is the magnetic poles? Actually, you must know if we suspended a magnet from a pulley, then it will be filled with irons. Okay, and we will get these types of. The strength of a magnet is concentrated at the ends called north and south poles of the magnet. So a suspended magnet, north seeking and as south pole also seeking and are north and south poles. So bar magnets will be like this and compasses will be this. So we have to use these compasses to find out the direction. Okay. Now, magnetic attraction and repulsion. This is the properties of, and unlike poles attract each other and like poles repel each other. This is the actually properties, main properties of magnetism. Now, what is the magnetic field? And that means magnetic line of forces. Actually, we can describe magnetic field or magnetic line of forces with this property by imaginary a tiny compass placed at nearby points. We get this one. So, and their direction also, which is called the magnetic field, capital B, at any points at the same and in the direction indicated by the compass. So the field B is strong where the lines are dense and weak where the lines are sparse. So this is the actually geometrical interpretation of magnetic line of forces. Now, the field lines between magnets. This is the unlike poles and leave and enter south pole. Okay, so this is the attraction, and this the like poles, the properties of line of forces of magnets for like poles, and this is the repulsion. So now what is the magnetic field? Magnetic field is the space around a magnet in which the force of attraction and repulsion due to the magnet can be detected by another magnet. And this is actually the properties of magnetism we have shown in our slide. And its SI unit is the Tesla, and it is also a vector quantity denoted by capital B. That means the magnetic field can be denoted by capital B, and it has both magnitudes and direction. This is why it's a vector quantity. So, what is the magnetic field lines and magnetic line of forces? Okay, the magnetic field lines are the imaginary curves which are used to represent the magnitudes and direction of the magnetic field at a place. So, this is the due to this magnetic field line of forces, magnetic field created. So, and we have also discussed about these properties with geometrical interpretation in our slide. So, it has we also discussed about their properties actually like this, and so their properties can be also discussed with like this. Okay, so we can also, so this is the magnetic field lines definition of magnetic field lines, and this is the geometrical interpretation. And we also the properties of magnetic field lines are this we have discussed. The magnetic field lines are closed and continuous curves. Okay, magnetic field lines they emerges from north pole and end into the south poles. So it has actually 6 and 7. Okay, 7 properties and properties of magnetic field lines. This is the density of magnetic field lines. The magnetic field, this is the electric field configuration, and this is the magnetic field flux lines pi. Line density can be denoted by is proportional to del n divided by del A. That means per electric field per area. Okay, so and capital B is the actually magnetic field, and this is the magnet south pole and north pole, and this is the line density for magnetic. So magnetic field B is sometimes called the flux density in which is measured in Webers per square meter, which is called also Weber. Okay. Now the magnetic flux density, magnetic flux are continuous and closed lines. Okay. It is magnetic line of forces. The direction is that of the B vector at any point. Flux lines are not in the direction of force but perpendicular. We have to remember it. So magnetic flux density, and this is the measured by this formula, capital B is equals to pi divided by A. Pi is the flux. Okay, magnetic flux, and this is the per unit area. When area A is the perpendicular to flux, then we can denote pi equals to BA. Okay, the unit of flux density is the Weber per square meter. Weber per square meter. Now calculating the flux density when area is not perpendicular. Suppose area is not perpendicular, area this area making theta angle with the parallel parallel lines of electric flux. That means flux penetrating the area A when the normal vector n makes an angle theta with the magnetic field B. Then this formula will be used. Pi equals to BA cos theta. So if theta is the 90 degree, then cos 90 degree goes to 1. This is why pi equals to BA. We got the previous formula. The angle theta is the complement of the angle A that the plane of the area makes the with the field B. So in that case, we can also use this negligible angle. That means cos theta equals to sine theta. Now origin of magnetic field. Okay. Recall the strength of electric field E was the defined as the electric force per unit charge. Since no isolated magnetic pole has been found, we can't define the magnetic field B in terms of the magnetic force per unit north pole. So we'll see instead that magnetic fields result from the charges in motion, not from the stationary charges or poles. This fact will covered later. That means from positive charge, electric field coming out, and the velocity v will be perpendicular to the magnetic field. Magnetic force on moving charge, actually, if we imagine a tube that projects a charge q, okay, q amount of charges, and this moving with a velocity v, which is perpendicular to the electric magnetic field b, then this experiment shows F equals to QBV. Okay, upward magnetic force F on a charge moving in B, each of the following results in greater magnetic force and increases in velocity B and increases in charge Q, a larger magnetic field B will be produced. So this force is called actually Lorentz law of forces. The direction of magnetic force, and this is the we can measure the direction of magnetic forces using using this right hand method. Now force of angle, and this deflection force greatest when the perpendicular to the field, least parallel, that means that is proportional to b sin theta. Okay, definition of b field, actually experimental observation shows the following: if it's proportional to qb sin theta, or it is constant, f divided by qb sin theta is a constant, and by choosing appropriate units of the constant of proportionality, we can now define the electric field, magnetic field b, as like this. Magnetic field intensity b can be denoted by like this, that means that goes to qbb sin theta. And a magnetic field intensity of 1 Tesla exists in a region space where a charge of 1 Coulomb moving at 1 meter per second perpendicular to the B field will experience a force of 1 Newton. So this is the main definition of B field. This is the example to measure application of this magnetic field formula. Now, force on negative charge, actually right hand rule. This is the left hand rule. You must know about this to measure the magnetic field B. Now, indicating direction of B field, a field directed into a paper is denoted by a cross X, uh, like the tail feather of an arrow, and a field. This also out of a paper is denoted by dot, like front of the arrow. So this is the actual indicating direction of vector field. In practice, we can use this up, and this will be left, velocity for negative and right. Okay. Now cross E and B also can be measured like this. The velocity of selector also. And this is the example for measuring the B field. This is the summary we have used. The right hand rules and for positive charge, and left hand rule will be for negative charge. We have to remember this. So this is the main formula, QBB sin theta. Actually, this is the formula. This is the formula of Lorentz formula, Lorentz force. Now we will discuss about, this is the ending of chapter magnetic field. Now, this is a great scientist who discovered the relation between electricity and magnetism in 1820. Henry Christian uh, Oersted performed an important experiment which showed that there was a connection between electricity and magnetism. Oersted found that when a current carrying conductor is placed parallel to its axis of a magnetic needle, the needle is deflected. Means to say, around every current carrying conductor, there is a small electric field. Okay, it is the perpendicular electricity I, and this is also. So if we place a magnet with south pole and north pole, and it will be deflected. So magnetic field due to current carrying a straight conductor. you have to remember these properties, which is Ørsted shows. Now, this is an experiment of Ørsted. And force factors upon the strength of magnetic field depends on current flowing through a conductor. That means B is proportional to I. Distance R from the conductor, inversely proportional. So now this is the right hand rule, thumb rule to find out the direction of magnetic field. Now magnetic field due to current carrying coil. Okay, this is the important conclusion for magnetic field line of forces. Okay, the magnetic line of forces near the coil are concentric circles. Okay, in the center of the this actually look like the by using the properties of magnetic line of forces. Now, what is the motion in a magnetic field? When a moving charge particle moves on a parallel direction to the magnetic field, then it does not feel any forces. The first case, when charge particle moves at a right angle to the magnetic field. Okay, just using the formula, sin 90 degree equals to 1. This is why F equals to UdV. This force is always perpendicular to the direction of the motion. And if we find out the relation between these two forces equal, this is the concentric force, circular path, then we get this relation R equals to mb by qb. Then the time period of revolution of the particle is this, so capital T equals to this one. Okay, now we will derive the important law of Lorentz law of forces. Okay, now we'll try to derive the Lorentz law of forces. Suppose a particle of mass m and charge q like this. Suppose this is the circular air and velocity b is moving, and there will be this is the actually field, electric field, and this is the electric field. So this is denoted by B. Okay, and this is the velocity B at this point, and this is the electric field, and this is also electric field, and this is also electric field. And this is the velocity B. So centripetal force will be created for this. This is the rotation, and with the velocity rotation of vector field. So and this is the magnetic field. So remember that this is the direction of B. This can be denoted by F. Okay, force, and this is the perpendicularly will be act this force. Okay, so within this magnetic field, this force will be produced. So the force on charge Q is can be calculated due to the magnetic field F equals to Q B vector cross B. And this can be denoted by Q B B sine theta. Okay, but this sine theta will be 90-degree because electric field and magnetic field will be the perpendicularly directed. This is why you can write QBB, F equals to QBB. This is equation number 1. And this is the linear force, okay? Linear force. Linear force. On the other hand, the force is always perpendicular to the direction of the motion and the magnetic field B. So the charge will describe a circular path. Here the force F provides the required centripetal force. And now centripetal force, centripetal force, centripetal force will be mass M B square by R. Okay. So M B square by R. So from these two equation, we can write from one equation 1 and 2, can write actually QBB equals to MB square by R. This is why R equals to MB divided by QB. This means radius of the circular path will be MB divided by. Now the time taken by the particle, time taken will be time taken to complete the circle, complete the circle, complete the circle. Capital T equals to what will be actually circumference divided by total traveling distance 2 pi r, circumference divided by this divided by B. Okay. This is equation number 3. Sorry, this is equation number 4. And this is equation number 3. So now using equation 2 and 3, we can find out capital T equals to using 2 and 3, 3 and 4. 3 and 4, we get capital T equals to 2 pi m divided by QB. Okay, so total time can be written as like this. So in this case, now if the charged particle enters into a region which both electric and magnetic field are present, so in that case we can find out total force will be if if the electric force F E equals to electric force, we can write QE. Okay, is the electric field. So electric force will be like this. So now total force capital F equals to electric force plus magnetic field force. Okay, magnetic fields force. So this equals to actually QE plus QBB. This is actually Lorentz law of forces. Lorentz law of forces. Okay, now what is self-induction? It is the property of a coil by virtue of which of the coil opposes any charge and the strength of current flowing through it by inducing an EMF in itself. When the current I is increasing, the self-induced EMF appears across the coil in a direction such that it opposes the increases. Therefore, it would be an direction opposite to I. That means increasing electricity is increasing, and here electricity is decreasing for the opposite direction. When the current I is decreasing, the self-induced EMF appears across the coil in a direction such that it opposes the decreases. Therefore, it would be in the direction self-inductance. This is the self-induction and this is the self-inductance. What will be the self-inductance? Let the current I flowing through a coil at any time, and electric flux phi is the amount of magnetic magnetic flux. Unlike with all the turns of the coil at any time, then it is found that magnetic flux proportional to the electric I. That means electricity. If electricity is increased, then magnetic flux will be increased. So we will get a constant for that phi equals to Li. So L is the constant of proportionality and it's called the self-inductance or coefficient of self-induction of the coil. So we have to remember these two definition. Now, if L equals to 1 and pi equals to, we get L. Okay. Self-inductance of a coil is a numerically equal to the amount of magnetic flux linked with the coil when unit current flows through the coil. That means the EMF induced in the coil is given by EMF equals to rate of change of magnetic flux with respect to time, and it is decreasing. That means minus means what? It is decreasing. So this can be the pi equals to Li from self-induction definition. So you can write EMF equals to minus L di by dt. And this is the very important law we'll discuss later. The SI unit of L is Henry. Electric inductance and self-inductance will be Henry. And this is the definition of 1 Henry. This is the example. So the definition of electromagnetic inductions, mutual inductance and self-inductance. This is very important definition. First of all, what is the mutual inductance? The changing current in the primary coil creates a change in magnetic flux through a secondary coil, which leads to an induced EMF in the secondary coil. Then the effects is called mutual induction. And this is the actually diagram for representing mutual inductance. We have what's the actually induction, you must know. Change in the magnetic field lines produced by a primary coil. This is the primary coil and this is the secondary coil, and a generator and a voltmeter to measure the electric current to potential difference. So this is the SI unit of mutual inductance is 1 Henry. Okay, mutual inductance is denoted by capital M. and self-inductance actually capital denoted by capital L. You must know in sorry inductance. This is also was a constant. Hmm. Now, what will be the self-inductance? So, the magnetic field lines produced by electric current I, the effect in which the changing current in a circuit induces an EMF in the circuits, same circuits is referred to as the self-inductance, and this is denoted by capital L, and its also unit will be same Henry. Now energy stored in uh, indicator will be denoted by this formula, energy equals to half L I square. This is the properties if a potential difference exists in the end of indicator, and this is the some example. Now, what will be the induced current? There are a number of ways a magnetic field can be used to generate the electric field. Electric field. So this is the actually, and there are a number of ways of magnetic field can be used to generate an electric current. Now, induced EMF. The current in a coil is called induced current because it is brought about by a change in magnetic field. Since a source of EMF is always indeed needed to produce a current, the coil behaves as if it were a source of EMF. This EMF is known as induced EMF. Now, ways to induce an EMF. An EMF can be induced by changing the area of a coil in a constant magnetic field. You have to remember it. And now, what will be the motional EMF? You must know F equals to QBB. This is a magnetic force for an for a charged particle within a conductor. Uh, the separated charges on the ends of the conductor gives rise to an induced EMF called motional EMF. So this is the definition of motional EMF, and this is denoted by motional EMF. When BBL are mutually perpendicular, then uh, this EMF equals to BBL. This is the example. Now, what is the magnetic flux? Flux is a mathematical term for how much of something is flowing through a surface, and it's virtually uh, more complicated but it is the simplest case of the magnetic flux in how much of the magnetic field is flowing through it, and we also discussed it in our previous lecture. Um, so, motional and magnetic flux, motional EMF. Magnetic flux equals to BA, and V is the magnetic field B, and A is the area induced. Now, a little this EMF equals to is denoted by uh, a magnetic flux per unit time, and it's decreasing. Okay, and we also discussed it in our previous one. So, and general expression for magnetic flux, this is the formula for cos phi, but cos 90 degree equals to 0. Remember that if this is the normal and this is the surface area. So B is the making angle phi to the normal. This is why formula will be BA cos phi. But remember that if they are perpendicular cos 90 degree, then flux will be 0. Okay. Now, the magnetic flux is proportional to the number of field lines that passes through a surface. Okay, more line of forces, more magnetic field lines will make strong magnetic field, and less will be weak magnetic field. So this is the actually graphical presentation, and this is the example. Now, what will be the Faraday's law of electromagnetic induction? This is very important for you. And Faraday's laws of electromagnetic induction, that what is EMF induced by a coil and loop is this. Okay, SI unit will be volt, and this is the an example. This is also another example. Now this is the Lenz law. Actually, the Lenz law, the induced EMF resulting from a change in magnetic flux has a polarity that leads to the induced current. The current will flow in a direction so as to oppose the change in flux. Use the combination with hand rule to predict the current. This is the main reason for the taking this one. Okay, now a famous scientist, Henry F. E. Lenz, the Russian physicist, uh, according to him, Lenz law is introduced. There are an induced current in a closed conducting loop if and only if the magnetic flux through the loop is changing. That means the direction of induced current is such that the induced magnetic field always opposes the change in the flux. So there, so what will be the Lenz law? There is an induced current in a closed conducting loop if and only if the magnetic flux through the loop is changing. The direction of the induced current is that of the induced magnetic field, always opposes. That means decreasing. A bar magnet pushed into a loop, increasing a flux through the loop and induces a current flow. Okay, this is the magnet, and magnetic field produces due to the magnetic line of forces, and this is the electric current meter to measure the electricity, and the direction of electric current is perpendicular to the magnetic field. Now, by using right hand rule, we can find out the direction of the current. And if you wrap your fingers around the coil in the direction of the current, your thumb points will be north. If the field of the bar magnet is already in the loop and the magnet is removed, the induced current is the direction that tries to keep the field constant. So, direction of the induced current, and if both cases the magnet moves against a force, work is done during the motion and it is transferred as electrical energy. So induced or always close to oppose the movement which started it. This is actually geometrical interpretation of Lenz law, and a bar magnet passes through a coil like this. This is the example you can study. This is also application of Lenz law. This is the linear induction. Okay, now we'll discuss the Ampere's law. This is a very useful law that relates the net magnetic field along a closed loop to the electric current passing through a loop, first discovery by Andy Mary Ampere in 1826. So we'll discuss what's the Ampere law. So Ampere formula, a law based on Oersted as well as Oersted experiment, as well as his own experimental studies. This law can be regarded as an alternative expression of Biot-Savart's law, which also relates the magnetic field and current produced, but it's needed an exclusively calculation of the curl of B, that means magnetic field. So Ampere's law can be states like this. The Ampere circuital laws states that the line integral of the magnetic field over a closed path or loop equals times the total current enclosed by the closed loop. We express these laws through the mathematical expression like this. That means line integral along the around the magnetic field B with the dot product with small length dl. This equals to will be mu naught I. And here I is the net current enclosed by the loop, and mu naught is the permeability of free space. It's the constant uh, which is value of 4 pi into 10 to the power minus 15 Newton per ampere. So this is the Ampere's law. Now Ampere circuit law also can be denoted by this. Then differential form of Ampere's law will be curl of magnetic field equals to mu naught Z, where Z is the current and CT. So we can represent these two types of form. Now there are many applications of magnetic field, Ampere's law. Now we'll try to derive the Ampere's law. Ampere's law. Actually, this is the line integral, line integral of the magnetic field dot product with small length dl. This equals to is proportional to I, and proportionality constant is mu naught here. So let us consider a conductor in which the electricity I is produced. Let us consider I current passes through the conductor. Passes through the conductor. Then for this, due to this current, a magnetic field will be produced. And if we place a magnet, then there will be magnetic field produced. So suppose there is this is the circular wire, and here this is the center, and the radius is r. Here if we take small length dl, and charge amount will also q. So due to this dl, there will be a centripetal force will be created, and magnetic field will be B, and this is the electric field radius. So due to this charge, this is the center. Now there will be create a torque. Suppose torque, you must know torque equals to torque tau equals to, can be written as you can write this is the P cross product with the magnetic field. That means we can write tau is proportional to B. So on the other hand, if the radius is on the other hand, we must know according to the definition of according to according to the definition of B, we must know magnetic field is the in proportional to the electricity I, but inversely proportional to the radius. That means distance. So this can be written as B equals to a constant constant multiply I divided by R. Now, if we take this constant equals to mu naught divided by 4 pi, taking where mu naught is the permeability of the medium, and which is equal to the 4 pi multiplied 10 to the power minus 7 Weber per ampere meter. So we can write B equal divided by R, taking constant equals to mu naught divided by 4 pi. This constant you must know from our previous slide. So this is equation number . And this equals to PB sine theta. This is equation number 1, and this is equation number 2. Okay. Again, we know by magnetic flux can be written as magnetic flux in a closed circuit. Magnetic flux can be written as small magnetic flux can be written as the dot ds. Okay. So magnetic field around the whole length of the circumference 2 pi r can be written as mu naught I. From Gauss law, we can write this from Gauss law. So this will be dl. Okay, dl. Now this is another equation number 3. So from this 2, now from this 2 we can write by using equation 2, we can write the line integral of B dl equals to mu naught I. This is actually our required derivation of Ampere's law in a short way.
the law. Why? Now, according to the vector, that so y equals to y small say I raise the small one. Now, according to the m, so this is the actually I unit about and this is the say. Okay. So at y, I is the y is the stop and b equals to 4 pi I